Good. So last time we saw that you can reduce the hydrogen atom problem, which is, I remind you, two particles, a nucleus and an electron, bound together, into a simpler problem, which is the relative motion of these two particles. So we introduced the center of mass, the total momentum, which was separated away, and we were left with the Hamiltonian, okay, for the relative motion that we wrote in the following way, is the relative momentum squared divided by twice the reduced mass, mu, minus z e squared over the relative distance x. Z is the charge of the nucleus, which could be 1 if it is a single proton, 2 if it is 2 protons, okay? So we can treat more complicated, but single electron hydrogen-like atoms, okay? Good. Now, we have to solve the associated time-independent Schrödinger problem. So we have to find the spectrum of the following problem: p squared over twice the mass minus z e squared over x applied to a wave function psi of the relative coordinate x equal to e times psi of x. Okay. Now, in order to further simplify, because x is a three-dimensional vector, okay, so x lives in R3. To further simplify the problem, we have to exploit rotational symmetry, okay, and in particular, we have to use the angular momentum. Okay, you know that angular momentum is fundamentally associated to rotations. So let's see, where is angular momentum, I mean orbital angular momentum, hiding? Where is it? It's in here, okay? It's hiding here. You see this p squared? Okay, let's analyze it better. Okay, look at the expression that we gave last time, well, a few lectures ago, about the total angular momentum squared, the orbital one. You see the expression is minus h bar square with derivatives with respect to theta and phi. By the way, from now on, to simplify a little bit my notation, I will put h bar to 1. This is not something I usually do, but I think it's better. Now, I urge you to go and look at your favorite electrodynamics book. This is the back cover of the book by Jackson, okay? Jackson. And you will find the expression for the Laplacian of a function, you see, in spherical coordinates. And I would like you to notice the following thing. There are two terms. The first term is involving radial derivatives. Okay, we'll see it later. Most interestingly, there is a second term, which is this part, okay, which involves derivative with respect to theta and phi. Do you recognize any similarity? I think you will recognize, given the fact that, notice, look at this term. You see that I have 1 over r squared, 1 over sine theta, the derivative with respect to theta of sine theta d in the psi, sorry, let me just do the calculation. Suppose that I want to do this derivative. I have two terms. One is from the derivative acting on sine, which gives me the cosine of theta times the psi in d theta. The second term is sine theta, the second derivative with respect to theta of psi. Okay, do we agree? Well, then this implies that this term has two contributions. One is 1 over r squared, the 1 over the tangent theta, the first derivative with respect to theta, and the other is the sine actually cancels with this, okay? And you get the second derivative with respect to theta, okay? The next term is just straight as it is, okay? Now look at your expression. You see, I have the second derivative, okay, which is this second derivative there in the expression for L², 1 over tangent derivative with respect to theta, which is this. And finally, this term here, which is 1 over sine square derivative with respect to phi twice, okay? The only thing to notice is that there is an extra 1 over r square everywhere, you see? Okay, here. Good. So in essence, the Laplacian contains the angular momentum in the derivatives with respect to theta and phi. Now, in the notes, you will find a nice way of discovering this, not as a pure calculus fact, but by just using a little bit of quantum mechanics and computational rules and things like this. But I prefer that you try to do it yourself and you accept somehow for granted the fact that when I have p square, remember p square is the kinetic energy, essentially apart from the mass term. This with h bar equal to 1 is equal to minus the Laplacian, okay? Again, because I'm taking h bar equal to 1. Now, this object here, according to Jackson and according to our understanding of the angular momentum, is actually written in the following way. So there is a term that is minus the second derivative with respect to r, minus plus 2 over r, the first derivative with respect to r, okay? And then there is another term that is plus 1 over r square, the angular momentum square, okay? So this term here is just what we see there. Notice there are a couple of minus signs that actually, so this minus sign here, you see, this minus sign here is actually embodied in the angular momentum, you see there, okay? So there is no need to put an extra minus sign in front, okay? While this sign here is opposite to what you see in Jackson, because I'm considering minus the Laplacian and not the Laplacian, okay? Maybe you are a little bit puzzled by the way I wrote this kinetic term, okay, with respect to this term that Jackson writes, okay? They are exactly the same object. I'll try to convince you of that, Okay. So suppose that you do as Jackson suggests, the derivative 1 over r square, the derivative with respect to r of r square times the derivative of psi with respect to r. Okay, let's do the derivatives. I have two things on which I can act, this or that. Okay, the first one gives me twice r divided by r square, and then I have the derivative of psi with respect to r. The second term gives me plus 1 over r square, the second derivative with respect to r twice. Okay, now you see that here I get 2 over r, and here I get just 1. Okay, so collecting the two things together, this is totally identical to second derivative with respect to r plus 2 over r applied to the psi. Okay, which is the way I have written it here. Okay, good. In fact, there are many ways of writing the subject, and in the notes you will find a further way. Okay, you can write it as plus an appropriate radial momentum square. Okay, never mind for that. It can be shown that there is the correct definition of a radial. Okay, the radial momentum. It's not the naive. The naive thing would be that the radial momentum is equal to minus I h bar, the derivative with respect to r. This is wrong. This object is not Hermitian. Okay, so what you need to write for an Hermitian radial momentum is a strange thing, which is this. Okay, this is the correct Hermitian radial momentum. And if you do a little bit of algebra, you will realize that this object is PR square, including the sign, obviously. Okay, so the full object that you see there is PR square. Okay, let's end this slightly dry story here, just to tell you. So let me just summarize the thing, saying that I was able to. Yes, please. Yes. Yes. I do not hear you.
I cannot hear you clearly.
Sorry, can you speak again? The audio is not very good.
I think I have a connection problem.
No, I can't hear your voice clearly. I mean, the audio is very, very bad. Can you try again?
Okay,
Now it's better.
no, I'm different. I'm different.
Oh, sorry.
Awesome.
Maybe,
maybe I talk.
Yes, please.
Okay. When I look at the bracket, you have written just up above the momentum. I see 2 over r has this side r, and it is not. It is now neglected in the bracket down, the equivalent part.
Here, I mean, what you mean is that here, I mean, let me just underline the object. You are asking why here I have 1 over r and here I have 2 over r?
No, I mean down. Yeah, exactly. 2 over r. Where is that side r going?
No, what I'm asking you is to verify that if you take the square of this object, you see here I'm telling you that this is the 2 over r comes in if you take the square of this. It comes as a mixed term. You know, when you do a binomial, you get a factor 2, okay? So this is not P over R. When I have the 2 over R, I'm not talking about the momentum, I am talking about the square of the momentum, okay? But never mind, if this story about the radial momentum confuses you, okay, just take it away. It's not important. The important thing is that the Laplacian in spherical coordinate has this radial term, plus or minus, depending on the sign, a term that is 1 over r square, the angular momentum square. Okay, this is the most important message of the story I've told you so far. Okay, so this is the actual important stuff. Okay, so let's go on. Remember that this is the ingredient in the here in the kinetic energy. Okay, so again in this piece here. Good. So I have now to use this information. And what is the best thing I can do since the angular momentum square actually enters there? I do separation of variables and I do the following thing. So separate, separation of variables. In spherical coordinate, obviously. So I write psi of x as some radial function. Do not confuse this with the center of mass coordinate, which we introduced last time. So it's some radial function, which depends on the distance from the origin, times a function of theta and phi. Guess what functions I will put? I will put the spherical harmonics. You might ask why? Because you know that L-square, okay, when you apply the spherical harmonics to it, what is the result? You remember by heart? I'll tell you, it's h bar square L times L plus 1, the spherical harmonic itself. In other words, the spherical harmonics are eigenfunctions of the momentum, of the angular momentum square, right? Because of that, a miracle happens if you substitute psi being a product of this kind. Let's see again the thing. So I recall, p square over twice the mass minus z e square over r over x times psi, okay? I write the psi as a radial function times the spherical harmonics, okay? I want this to be equal to some energy times the radial function times the spherical harmonics. I omit the theta and phi, okay? Because, I mean, it's obvious. Now I notice that this object, p square, I told you, is equal to, let's put back the h bars, okay? It's minus h bar square times, I copy, second derivative plus 2 over r d in dr. So second derivative plus 2 over r d in dr plus L square multiplied by 1 over r square. Okay, so this is the crucial thing that I discovered from carefully looking at Jackson and interpreting correctly the ingredients that I find there. Very nice. Now you see that when L² acts on the spherical harmonics part, it gives a very simple result because of this crucial equation. Okay, so let's try to spell out the result of the equation star. Okay, so the star now becomes, so I have minus h bar square, second derivative with respect to r of the radial function, plus 2 over r, the first derivative with respect to r of the radial function, okay, times obviously the spherical harmonics, okay. Obviously there is a factor twice the mass.
Sorry, Professor.
Yes.
I don't get where the term the L² comes from in the expression of P².
Oh, it comes from either from a careful look at the lecture notes and doing the algebra that I proposed there, or from a careful look at Jackson expression for the Laplacian in spherical coordinate. You notice that the derivative part that involve the angles theta and phi are precisely, apart from this factor 1 over r square, precisely the objects that appear in the expression for L² as we have presented in our lecture on orbital angular momentum. Okay.
Yeah.
So the idea is recognizing the ingredients. Okay.
Yes.
So inside this expression that Jackson gives, there is in fact 1 over r square L². Okay.
Yeah.
And I'm rewriting this in this form just to underline that L² appears in the Laplacian. Okay.
Okay.
Is it clear?
Yes. Thank you.
So this is a crucial thing because I now use spherical harmonics, which are eigenfunction of L², to simplify the algebra in a very remarkable way. Okay. Good.
Hello, Professor.
Please.
Yes. So apart from just looking, of course, in the algebra, we can, which you clearly explain, is good to first of all see this and realize that the angular momentum squared is actually in the Laplacian. But also, what if we think about it from the idea of just purely classical mechanics? I remember like when you introduce angular momentum, from the basis of classical mechanics is the R component cross the momentum.
Absolutely so. Yes.
Yeah.
You're perfectly right.
Yes.
Yeah. And this is precisely what I was suggesting. If you read at the beginning part of page 86 of the notes, okay?
Yes.
There is in particular a footnote which shows you that if you calculate, so let me open this aside, okay? So maybe I just move it somewhere down here. Okay, sorry. I make this aside. So if you consider L² in classical mechanics, remember I have some distance from the origin, and I have some momentum. Okay. Then what I have is the component of momentum perpendicular to the distance. Okay.
Yes, exactly.
L² is equal to R² times the component of momentum square, the perpendicular component. Okay.
Yes.
You can write this as R² times the full momentum minus the parallel component square, which is this.
I see.
Okay.
Yes.
If you do this algebra, you will realize that this is R². The P square, because this is the component square, this is p vector square, so the length of p, minus x dot p, which is the component along
The parallel component.
square. Okay?
Yeah.
So this is
Yes.
class. So you see that
Mm.
the Laplace somehow, which is p square,
Comes-
suggests
Uh-huh.
the only missing term is that this expression is actually imperfect. If you do the algebra correctly, you will get an extra term that is plus I h bar x dot t. Okay?
Ah.
This is the quantum part.
Mm.
Okay?
Yes.
And the algebra in the notes explain how to get this extra piece. You see, for h bar equal to 0, you don't get it. So
Yes.
in classical angular momentum, you don't find this object.
Oh,
But
I
in the
see.
quantum, yes. Okay? So
Yes.
this is just footnote number 2, and the algebra is on page 86 of the notes. Okay?
Yes, this is okay. Thank you.
Okay. Let's return to our story. Excellent. So I applied the first part, the radial part, and I apply it to R. Okay? Then I have the angular momentum part. Okay? So I have what? Remember, p square is equal to, I go back, this radial part with the minus sign and this 1 over r square L square. So I put now plus 1 over r square. I have this 1 over twice the mass to keep track of. And then I have L square acting on r times psi. So r gets nothing, but L square applied to y, okay, will give me a contribution, right? And then I have, and this is the full, so this is the radial part, this is the angular part, and then I have what? I have the Coulomb potential term, right? So I have minus z e square over the distance. So I have, well, this is r really, times r times y lm. Now this object should be equal to E times R times Y Lm. Okay, I'm just substituting the separation of variables for the wave function. Okay, is it clear so far?
Yes.
Okay, well, maybe it's
Professor,
better if someone does not understand what I'm doing, please stop me.
Professor,
Yes.
I have a question. So about the definition of the radial momentum. When I try to square it, it has an additional term of 1 over r squared. So
It is cancelled. If you do it properly, you will see that there is a derivative term, the derivative of 1 over r, which cancels this this 1 over r square. I skipped the algebra, but if you do it correctly, you will see that it is actually correct.
Okay, thank you.
But don't get distracted now by doing extra algebra, which is somehow not relevant. This is maybe some afternoon thing that you can do, okay? Good. So I'm doing my separation of variable exercise. And now the crucial thing is that L square applied to the spherical harmonics gives me h bar square L plus 1 times the spherical harmonics. Okay? So let me just, summarize the result in the following way. Maybe I just write it here. So I have minus h bar square over twice the mass, the second derivative of the radial function, plus 2 over r, the first derivative of the radial function, multiplied by y lm, plus h bar square over twice the mass, 1 over r square, and then I have L plus 1, and then I have R times Y Lm minus Z E square over R times R Y Lm equal to E R Y Lm. Okay, is it clear? This is the algebra of substituting the psi written as a radial function times a spherical harmonics, done totally, okay? And just remembering that the Laplacian contains the angular momentum. Is it clear so far? If someone has doubts, stop and ask. Otherwise, I assume that everything is clear. Now you see that Y, you see it appears, the spherical harmonics, they appear here, 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 and here. But there is no longer any derivative with respect to theta and phi to take care of, okay? So in fact, they are just spectators, right? So since they are spectators, let me just cancel them. So I cancel the Y, okay? And what I get is a radial equation, okay? Radial equation. The radial equation reads just what you see there without the Y, okay? So let me write it again. The radial equation reads as follows: minus h bar square over twice the mass, the second derivative with respect to r of the function r, plus 2 over r, the first derivative. Then I have a term that is, you see, there are this 1 over r square, which I have to remember, and then there is this 1 over r comes from the Coulomb. Let me put them together. So these two terms, they read like that: h bar square L plus 1 divided by twice the mass r square minus z e square over r, and this multiplies the function r, okay? And all this has to equal the energy times the radial function, okay? Is it clear? This is the radial equation. Now you see that the angular momentum gives a contribution to what you might call an effective potential, okay? You see that the effective radial potential contains the Coulomb part and contains, for L different from 0, what is called the centrifugal part, okay? So this extra contribution, physically, the meaning is the following. If I plot versus r is the distance from the origin, the Coulomb potential is attractive and it goes to minus infinity, okay, when r goes to 0. This is Coulomb. Now, if L is different from 0, there is an extra diverging contribution, which I plot here. Okay, this is for L different from 0. Okay, and it goes like 1 over r square. So can you tell me what happens when r goes to 0? You find something like this. The sum of the two terms goes like this. Okay, sorry, it's not particularly well. Well, you understand, right? It's a bit ugly, but you understand. So this tends to push away, okay? Push away the electron from the origin. okay, physically. Good. But otherwise, looks like an equation for a problem in one dimension. Well, not quite, right? If you look at this expression, there are a couple of strange things. The first strange thing is that I have this extra term, 1 over r, this first derivative with respect to r. I mean, this is not a standard Laplace, a standard momentum in square of momentum in 1D, right? This is what you would write if I were to write a one-dimensional Schrödinger problem, right? This is strange. The second strange thing is that the normalization, so the normalization that I should impose is indeed the following. I should impose that the integral in dr from 0 to infinity with the factor r square, and the integral from 0 to pi in d theta sine theta, and from 0 to 2 pi in d phi of the r square times ylm square. This is equal to 1. Is it clear? This is the normalization. Remember that in 3 dimensions, when I integrate, I need this r square, okay? And then I have the angular integral with the sine theta and so forth, all right? Now,
Sorry?
please.
What do you mean by saying I push it away the electron at R0?
Well, you see that there is a repulsive potential. The potential is strongly repulsive close to r equal to 0. So the Coulomb attraction would like to pull the electron towards the nucleus. But this L different from 0 term actually pushes it away because there is a repulsive potential. You see the thing? There is a repulsive part. This object is repulsive. You go towards the origin and the potential increases. Therefore, you don't, I mean, it's like a wall. Is it clear? We will see that functions for L different from 0 tend to be less, tend to have less charge close to the origin because of this repulsive effect. It was just a little bit of physical intuition, nothing really special. Don't worry. The algebra will clarify the thing, but I wanted to somehow tell you a little bit of story about the physical intuition of this L-dependent term. Is it clear? Yeah.
Sorry, Professor.
Yes.
I remember in the note when we discussed angular momentum, and we started to look at, although what we looked at was just the radial component, the y lm, and we tried to look at that and see how that component behaves, how that harmonic behaves when we are at 0, 0. And they're not stated, in which we can also follow intuitively that this is trivial and also sort of warps around all through space. If we in this equation, if we look at the radial component in this equation and we assume that L equals 0, I think that it now shows us particularly that if we would think about L equals 0 for the s orbital in a way that there is some sort of attraction. So in reality,
attraction. S states are attracted towards the origin, and therefore the ground state, in fact, the ground state is the one that gains more of the Coulomb attraction. Obviously, you don't go to the origin because there is kinetic energy. So there is a balance between kinetic energy and the attraction from the nucleus, and the S state comes lowest, and it is the ground state, the famous minus 13.6 electron volt ground state of the. Okay.
Yes.
It's precisely correct.
Yes.
Good. So let's, Let me go on. Now you see clearly that the integral over theta and phi of the y square is totally irrelevant because the spherical harmonics are already normalized to 1. So the condition that I want on the r is that 1 is equal to the integral from 0 to infinity of r square modulus of r square. This is not a standard normalization because, I mean, not standard, say, 1D normalization, okay? Because of this factor r square. So there are a couple of things that make this radial problem not a standard one-dimensional problem on the half line, okay? I would like to reduce myself to a standard Schrödinger problem in one dimension in this half line 0 to infinity are belonging to 0 plus infinity. But there are these couple of strange things, okay? Well, the solution is the following. It's a very remarkable thing. Notice that here I have r times the radial function, okay? Let's change variable and I define a new function, which is u of r, which is the product of r times the radial function of r, okay? Now you see immediately that in terms of u, the normalization would look integral in dr of u of r modulus square equal to 1, okay? So it looks a normal, a standard 1D. The
Sorry?
even more remarkable, yep.
How to get one from the integral of sine theta and y ln squared?
This is the angular integral. By definition, the y are normalized. The y lm are normalized in precisely this way. So in other words, this integral of y modulo square is 1. By the way, they are normalized by y normalization. Okay? So you don't have to worry about the theta and phi because the y take care of making the integral equal to 1. You only have to require that the radial function is normalized. And the radial function normalization reads like this. Is it clear?
Yes.
Good. Now I define this new function, which is the product of r times r, and it looks like a trivial thing to do, right? I just get u squared. Fine. Now look at the very interesting algebra. You see this object here, okay? It is a remarkable fact that if you calculate the second derivative with respect to r of r plus 2 over r, the first derivative of r, this can be also written in the following way, as 1 over r, the second derivative with respect to r square of the function u. Remember, the function u is r times r. Okay, this is the u. Now you might say, hey, where is it? Okay, so you can just verify, okay, that the algebra is perfectly right. If you try to do the second derivative of this equation, do it in the afternoon. Don't do it now. So it is a remarkable fact that you can write it in this way. Okay, good. If you do this, then you realize that your strange kinetic term is in fact now much better. Okay, so let's reconsider our radial equation. So this equation here in terms of u. Okay, so radial equation in terms of u, which is r times the radial function. So I do the algebra. Okay, so I notice that the first term is minus h bar square over twice the mass. I told you that I can write this as 1 over r, the second derivative with respect to r square of the u function, right? Then I have, what else? Plus h bar square L plus 1 divided by twice the mass r square minus z e square over r times what? Here I see the function r, right? But the function r is u divided by r. Okay, very good. All this should be equal to, let's see again our equation, e times the function r. E times the function r, which is u divided by r. Okay? And now you see, beautifully, you see that there is a factor 1 over r everywhere, which is a spectator again. Fantastic. I get rid of it. Okay? So the final equation now looks minus h bar square over twice the mass, the second derivative of the u function with respect to r, plus this object. I rewrite it for the last time. It's always the same thing. Times the u equal to e times u. Now, this is the radial equation for u. It looks absolutely as a standard problem so a standard Schrödinger equation in 0 plus infinity, including the normalization, because the normalization is, remember, that integral from 0 to infinity in dr of u of r modulo square has to be equal to 1. Okay? So we have reduced ourselves to a radial problem which looks standard in the sense that our kinetic energy is our beloved minus the second derivative. Okay? The only thing to remember is that if I have L different from 0, the potential, okay, contains an extra term that is essentially 1 over r squared times the angular momentum of the particle. Okay? So in some sense, this already tells you that this function u that I write should have indices, right? What index should I put? I should put an index L for sure. Okay, so where you see u, think of u with certainly L. L, the index of the angular momentum wave functions, the spherical harmonics, I should keep. But there could be also other indices. Let me call K to distinguish the different solutions. Okay? So in general, I will have u of KL. This is some extra indices to distinguish the solutions. We will see in a while that these are integers also, but for the time being, these are labels, okay? The important thing that L is the angular momentum, okay? So L could be 0, 1, 2, or whatever, okay? Obviously, where you see E, you should think of E, OK, and L, right? Okay, that's it. We are now to a standard, arrived to a standard problem in 1D. Notice also one remark. The fact that the Coulomb potential was 1 over R, or better, the potential was 1 over R, is almost never used. Okay, so any Coulomb, any radial potential, so if this was any radial potential, would do. Okay, you could put any radial potential there and the algebra would be totally identical. Okay, so far we have not exploited the fact. Okay, so remark, any V of R would give the same algebra. Okay, fantastic. Now we want to solve this problem. Okay, and you see that there are lots of H bars, the mass, the charge of the electron, lots of things that are rather annoying. People sometimes say, okay, let's put H bar to 1, mass to 1, E to 1, everything to 1, okay? But then you start feeling uncomfortable and asking, well, yes, but if I have to produce a number, what should I do? And you know that the correct procedure, or I mean, the procedure by which you can extract dimensionless variable is always similar. So let me find a length, define a length A, I call it A. It will be the Bohr radius in a while. You will see the Bohr radius. But so far, I don't know. I just pretend that the Coulomb energy associated with this length A, this is the Coulomb energy. Okay, simply the potential energy felt at a distance A. I pretend to be equal to the kinetic energy of confining a particle in a length A. Notice that I don't put the factor 2 there, okay? Obviously, you might say, well, let's put the factor 2. No, if I don't put the factor 2, I get the Bohr radius. Otherwise, I get a slightly different length, which you could use, but it's not the conventional length. There is a reason behind that, but never mind. Okay, so this is the kinetic term, kinetic energy. Very good. If you solve this equation for A, you find A equal to h bar square over the mass E square divided by Z. Okay, this object is called the Bohr radius. Okay, so A comes equal to this important quantity which contains the important universal or material physical constant, h bar, the charge of the electron and the mass of the particle. All right, and also the number of protons. Fantastic. Now this length is the crucial length. So I want to measure rather than R, I define a dimensionless variable rho, which is R divided by the Bohr radius. Okay, this is a dimensionless length. Okay, I could define all dimensionless quantities. In particular, notice the typical energy associated to the Bohr radius. Let me call it EH. So Z E squared divided by the Bohr radius. It doesn't matter which one you take. You see, for the Bohr radius, these two things are exactly the same. So if you calculate Z E squared over H bar, you find mu e to the fourth z square divided by h bar square. This quantity is called the Hartree, okay? Is the Hartree. And this numerical value is, for z equal 1, 27.2 electron volts. So sometimes in the papers, you will be finding things and you will find the abbreviation AU, which stands for atomic units. Atomic units are the units in which lengths are measured in terms of the Bohr radius and energies in terms of the Hartree. Okay? So this is the dimensionless variables that you need to do. If you rewrite the radial equation for U in dimensionless terms, in dimensionless form, you get, okay? The algebra is very simple, done, alluded in the notes, but it's very, very, very simple. So I will define the function u tilde of KL as a function of the dimensionless variable rho to be, never mind for the normalization, I will tell you in a second, is u of KL calculated at r equal to the Bohr radius times the dimensionless length rho. The correct normalization is the square root of AB, because if you change variables, okay, remember that also in this integral, okay, you have to change the correctly the variable and you get the square root of AB factor. But that is not particularly important ingredient because it's an overall constant for the function. The interesting thing is that you get minus 1/2 the second derivative of u tilde with respect to rho 2 times. This is the kinetic term. You see h bar has disappeared, the mass has disappeared, plus L plus 1 divided by twice rho square minus 1 over rho u tilde of KL equal to E tilde KL U tilde KL. Now, notice here, no H bar, no mass. Here, no E, no Z E square. Okay? Very nice simplification. Notice also this object here. This is the energy. So E tilde is equal to the energy in units of Hartree, which means divided by the Hartree. Okay? This is the final equation we should in principle solve. Okay? Clear so far? Good. Shall we make just a couple of minutes break so that you can think of possible questions? Okay. Okay. Sorry, I drink something. Okay, let's start again. Now, here in the notes, you will find some details, okay, which I will try to summarize here for a couple of reasons. First of all, we have no time. Second, it's hard to do a lot of algebra here on this iPad, okay? So I prefer to somehow refer to the notes. So the thing that I would like, I have this function u tilde. By the way, let me omit the tilde, okay? So u tilde KL of rho, I call now u of rho, okay? Forget about indices, tildes, and things. Okay, the second thing, I would like to know, first, what happens for rho going to 0. The second is what happens for rho going to infinity. After all, I'm working with rho in the interval 0 infinity, right? And I would like to know what happens at the limits of this interval. And here you can show the following nice thing, that for rho going to 0, the fact that this equation makes sense commands the fact that u of rho will go like a constant times rho to the L plus 1, okay? This is a requirement for essentially these two terms to somehow compensate each other nicely, okay? Look at the notes and make sense of this discussion in the notes. Now, the second aspect of the story is the fact that for rho going to infinity, you can prove that in order to have a bound state, I recall you that the bound state is a state that is actually normalizable and somehow concentrated in a volume around the origin, okay? So it's not a wave that escapes away, okay? So in order to have a bound state, then the u of rho for large rho behaves like e to the minus some lambda rho, okay? Obviously, this lambda, okay, is in reality depending on the k and the l, all right? Good. Now, these two things come rather simply by looking either at the kinetic term versus the centrifugal term, or by just looking at the kinetic term for very large distances versus the E term that you have there, okay? I will not present this algebra here, which is given in the notes, but I would like to carry out with you a very, very simple calculation. Let's put L equals 0, okay? So I know that the function should go like, so let me write a function which satisfies these two criteria. So for rho going to 0, okay, it goes like rho, because for L equal to 0, you see I have L plus 1 equal to 1. For very large distances, I have the exponential. So I put e to the minus lambda rho. Okay, this is my candidate function. Okay, so I do a little bit of algebra. I substitute in the Schrödinger equation. I remind you that the Schrödinger equation is this, right? So I should do minus 1/2 the second derivative with respect to rho of this object, A rho e to the minus lambda rho. And then I have plus L is equal to 0, so nothing. So I have plus, oops, sorry. I have really a minus 1 over rho times A rho e to the minus lambda rho equal to E, sorry, equal to E A rho e to the minus lambda rho. This is what I would like to see. Is it true or not? Okay?
Sorry.
And yeah, please.
How did you get U of rho?
U of rho, I invented. It's the simplest function that it has the right behavior close to rho going to 0, which is this, okay? Which again, I urge you to look at the notes why it should be like this. So for L equals 0 should go linearly to 0, okay? And for large distances is exponentially decreasing with a factor lambda. Okay? This is the simplest function which incorporates the two ingredients. Just multiply them and you have a function that goes to 0 linearly, rho going to 0, and it goes exponentially to 0 for very large distances. Okay? It's a guess, a candidate. Okay? A guess. That's the reason why I put the question mark. Is it true that this equation is correct? Okay.
So the kinetic part goes to 0 automatically?
No, I mean, not the kinetic part. The U goes to 0. The kinetic part is this. You have to calculate the second derivative. I don't understand what you mean by kinetic part.
I see, I see.
All right, kinetic part is second derivative, okay? You should do the second derivative of this guy, okay? If you do it, okay, try to do it, you will see that the only possibility, first of all, A cancels totally. You see, in this calculation, A doesn't matter. A will fix the normalization. You have to do the second derivative of this guy, okay? Shall we do it? Let's try to do it. Otherwise, everything seems a miracle. Okay, first derivative. I take the first derivative of the rho e to the minus lambda rho. So I get e to the minus lambda rho plus rho times minus lambda e to the minus lambda rho. Okay? And then I have minus. By the way, the rho and rho cancels. So minus e to the minus lambda rho equal question mark e rho e to the minus lambda rho. Okay, I proceed. I do an extra derivative, minus 1/2. I get a factor minus lambda coming, e to the minus lambda rho, plus I do the derivative of the rho here, and so I get minus lambda e to the minus lambda rho, plus I do an extra derivative of the lambda, and I get rho minus lambda squared e to the minus lambda rho. Okay. Then I have minus e to the minus lambda rho. And this should be equal, question mark, to e rho e to the minus lambda rho. Okay. So first of all, you realize that e to the minus lambda rho appears everywhere. So I can get rid of it. Okay. So I noticed that these two terms are exactly the same. So I get the factor 2. So I rewrite minus 1/2. I get minus 2 lambda plus rho lambda square. Okay, then I have -1. This should be equal to E times rho. Okay. Shall we write it even better? I write minus lambda square over 2 times rho. Then I have a term that is plus lambda, which comes from here, -1 equal to E times rho. Is this an equation that makes sense? It makes sense if I take lambda equal to 1, which means that this object here is equal to 0. So because there is no constant term in the right-hand side, and I take E equal to -1/2. You see, if you take these two, huh? Well, lambda is equal to 1, and the square root of 1. Okay. This is the square, in fact, is the square. So if I take lambda equal to 1, I get a solution. This solution is, in fact, the ground state of the hydrogen atom, because it's minus the R3 divided by 2. Remember that this is E tilde, really, the dimensionless energy. And this is minus 13.6 EV. Okay? So this is, in fact, and the lambda equal 1 means that the function that I get is an L equals 0 function, first of all, and it is such that it is equal to A rho e to the minus rho. Now you might say, hey, what is this? Well, it is equal to A rho, which is R divided by the Bohr radius, times e to the minus R divided by the Bohr radius. Okay? And you might say, what is this? This goes to 0. Yes, but remember that U was equal to R times the radial function. So if I write the radial function associated to this L equals 0 state, I find some A times no R e to the minus R EB. Beautiful, okay? It is a decaying exponential. So the radial function of this, it is called the 1s state, by the way, okay, is simply a decaying exponential. And as I promised, it is more concentrated towards the origin because the S state have L equals 0, and they like to stay close to the origin. Obviously, not all in the origin, okay? So you accumulate a little bit towards the origin, the peak is there, but then you go decay. Is it clear? Now, this is a very simple thing. I just guessed the state and I verified that it works, okay? Obviously, now comes the worst part of the story. I can guarantee is absolutely the most boring calculation we have done so far. And there is, by the way, not a very long time. So I propose that you try to, I'll give you the idea, and you try to fill out and do the algebra yourself, okay? So now the algebra. So I want to solve algebra to solve the radial equation. Okay, it's done on page, say, 89 of the lecture notes. Now you do the following. You take U, I remind you, it had two indices, K and L, and you write it as a polynomial times e to the minus lambda K L rho. Okay, since I know that at very long distances, it should go exponentially. Remember fact number 2. This was fact number 1. Okay, since I know that it must go exponentially, I put the exponential inside. Okay, the rest is a polynomial, and I know that this polynomial, in fact, should start in a very precise way. This polynomial or function of R should start like rho to the power L plus 1. This is fact number 1 here. You see? Very good. Well, rho to the power L plus 1 times what? Times anything. So a constant plus C1 rho plus C2 rho square plus anything you might want. Not only a polynomial, in fact, an infinite power law I allow. Okay? So I write this as the sum over some integers q going from 0 to infinity of some CQ times rho to the power Q plus L plus 1. Obviously, the L plus 1 comes from this, right? While the Q takes care of all other terms. The C0 is the constant, C1 is power 1, C2 power 2, and so forth. Is it clear? This is my ansatz. Okay, so I write now a much more flexible ansatz. Okay, ansatz, which is my guess. The guess is now parameterized by an infinite number of constants, which I don't know, C0, C1, C2, and this lambda there, okay, which I don't know. Okay, and I want to see if I can solve the problem more generally. Okay, this is the goal. And the answer is yes, it can be done. Okay, so try to follow the algebra, and I would skip at least 2 or 3 steps, which are useful and instructive in many respects. But I think that it would be just too long and too boring for you to actually. Let me just give you the ingredients you need. You see, I need to calculate. Remember the radial equation. I need to calculate the second derivative, okay? And the other terms are simple. So I need to calculate, first of all, the second derivative with respect to rho of W times e to the minus lambda rho, okay? So if I denote, if I do this algebra, I will obtain something like this. I mean, I will obtain second derivative let me put the factor minus 1/2. If you do the subject, you get the following thing. So minus 1/2, the second derivative applied to rho only. Then you get a plus lambda, the first derivative. Okay? And the whole thing is multiplied by e to the minus lambda rho. Okay? The idea is that the exponential survives. Okay? So if you take derivatives, you can bring down some factors. Okay? But the exponential survives. Okay, now if you use this fact, you will see that as usual, the exponential is the spectator. Okay, so you can erase this exponential from your equation, and your equation would look like the following. So minus 1/2 the second derivative of W, so the power law part, plus lambda, the first derivative of W, plus L plus 1 over twice rho square minus 1 over rho W equal to 0. Nicely enough, there is a cancellation if you assume that lambda KL is equal to the square root of minus twice E tilde KL. Okay? So if you take the lambda to have this form, you will see that the term with A, which comes essentially at the expense of a lambda square. Sorry, I think that I missed here some lambda square term. Okay, I wanted to make the algebra more, faster, but I mean, this is probably a bad idea. So I urge you to actually do the steps in page 89, okay, carefully enough yourself. Otherwise, there's essentially nothing that I can do to convince you of the fact that you can do this algebra, okay? So, well, at the end of the day, by using the expression for W, which I remind you is a power law, you see, it's written like this, you find equations for the coefficient CQ. They look as follows. So equation for the coefficients CQ. Minus 1/2 the sum from Q equal to 1 to infinity of Q plus 2L plus 1 times CQ times rho to the power Q plus L minus 1 plus sum from Q equal 1 to infinity of lambda KL Q plus L minus 1 times CQ minus 1 rho to the Q plus L minus 1 equal to 0. Okay? This is the equation that you get after doing a little bit of algebra. Okay? Very, very boring, but it can be done. Okay? Follow the notes. Now, one thing that you notice that here you have two infinite sums, but they have exactly the same coefficients. I mean, the same powers of rho. Rho to the Q plus L minus 1. You notice? Which means that these objects can be 0 only if term by term the coefficients actually match. Okay? So this coefficient here, okay, has to match this coefficient here. And this is a very beautiful equation because it relates CQ, which is what you see here, to CQ minus 1. Okay? If you do impose that these two coefficients are actually, I mean, one opposite to the other, in fact, so that you get 0, you will find an equation now of this form. CQ has to be related to CQ minus 1 in the following way. Twice lambda KL times Q plus L minus 1, which is this object here, you see, divided by Q times Q plus 2L plus 1 times CQ minus 1. Notice that the denominator is precisely what you have here, okay, including the factor 2, which is here. All right, so this is the final, almost final equation that we have. I know the coefficients in a recursive way. There is a recursive formula for the CQ. So if I give you C0, you produce for me C1, and then from C1 you produce C2, and then from C2 you can produce all coefficients, okay? So I know the function completely. But at this point, remember that lambda is actually related to the energy. Lambda, if you want, lambda square of KL is equal to minus twice the energy. Remember this expression that is essentially given here. Again, is inside the algebra, so it's well hidden. Okay, very good. Now it seems that you can
Professor?
find. Yes, please.
Can I ask you why you need to impose lambda squared equal to minus 2?
No, you cannot ask, unfortunately.
I mean,
No,
I
no,
think the algebra that you move the thing to 0. But I don't get why you need to make it 0.
No. It is only clear if you do the algebra. If you don't do the algebra, you will not catch it. Okay? It is, in fact, it is strongly related to this point here. Okay, this point tells you that if I have a function that goes like e to the minus lambda rho. So let me explain to you. Suppose that I am a very, very, very large rho. Okay, so very large rho, where the function, okay, u is essentially e to the minus lambda rho. Okay, so I do have minus 1/2 the second derivative of the function plus what? There are things like L plus 1 over rho square minus 1 over rho times the function, okay? But these are smaller, okay? So you see that these are things that are much smaller than E times U. E is a constant, and these are smaller. So let me just forget about this term and keep only E, okay? So you realize that when you disregard these little terms with respect to E, in other words, I'm writing here that the second derivative, bring this on the right-hand side here, this should be equal to E minus L plus 1 divided by rho square, whatever, there is a factor 2 probably, plus 1 over rho, okay, times U. This is the equation you have. Minus 1/2 the second derivative equal to that. Now, for very large distances, this and that should not matter. It's only E that matters. But if you calculate the second derivative of this object here, you find minus 1/2. The first derivative gives you, sorry, the first derivative gives you minus lambda, e to the minus lambda, okay? Then you calculate the second derivative and you get minus 1/2 minus lambda square. times u times e to the minus lambda. Sorry. E to the minus lambda rho. Okay? So you see that in order for the two objects to match, the energy and this object here should be precisely the same. So the energy of the bound state should in fact be minus 1/2 of the parameter lambda squared. Okay? There is no other way that this equation can actually be satisfied for very large rho unless the energy is the square of the parameter lambda that you put in the decaying exponential divided by 2. Okay? So that's the reason why I am all the time giving you this fun equation. It's always the same equation, and is fundamentally related to the large rho behavior of the function. Okay? Is it clear? A bit more clear. So it is, in some sense, details of the algebra, but in some other sense, there is some physics in it. It's only the decaying exponential that controls the bound state value. Okay, the energy in the end is minus 1/2. It's a bit like a k squared over 2. Okay, but with a negative sign, because this is not a plane wave, it is a decaying exponential. It's always the same factor, by the way. Okay, good.
Okay.
Given all these details, more or less, you realize that still, where is the bound state? Every energy, so every lambda, I can solve this equation, right? And find, given C0, you decide C0, I find for you C1, C2, blah, blah, blah. So quantization, where is the quantization? I expect that there are some states at precise energy eigenvalues, and all the other states are not allowed. Why is that? The solution is hidden here. You see this factor? Generally speaking, the CQs are all different from 0. All different from 0. Up to C infinity, okay? An infinite number of constant. Now, this, it turns out, is not a good thing. The only way out is the following, that this factor here becomes 0. In other words, suppose that for a certain value, suppose that for a value q equal to some integer k, the lambda kl times k plus l minus 1 is exactly equal to 0. Then what happens is that, as a consequence, ck is equal to 0, although ck minus 1 is different from 0. Okay? You realize that this is a miracle that makes this infinite power law a polynomial, because the term with ck is equal to 0, and then from there on, all the other terms will be 0. So there will be only k minus 1 terms in this infinite power law. But this happens only if I have this crucial thing. Okay? Let's explore this fact. So suppose that indeed I have a value of k greater or equal to 1, and that lambda kl times k plus l minus 1 is equal to 0. What does this imply? it implies that lambda KL is equal to 1 divided by K plus L. But K is an integer. It's in fact an integer greater than 1. L is an integer. In fact, L could be 0, 1, up to infinity, right? So this object is 1 over an integer. Let me call it 1 over n. So n is the sum of k plus L. Okay? Good. Now remember that the energy, or better, the energy in terms of the Hartree, was equal to minus 1/2 the square of lambda. Okay? Well, then this is equal to minus 1/2 1 over n squared. Okay? And this is precisely the tower of eigenvalues. So this is the eigenvalues. This is 0. By the way, for positive energy, I have unbound states, a continuous spectrum, scattering solution. We don't care about them. Okay, these are scattering solutions, which is not what we were hunting for. What we hunt for is this minus 1/2 1 over n squared. By the way, for n equal 1, we get minus 1/2, the value that we just calculated with the gas, the very first gas. Okay, so here it is, minus 1/2, the ground state. Then I have minus 1 for n equal 2. What do I get? N equal 2, I get minus 1/2 times 1/4, right? So I get minus 1 over 8. So something here. Okay? And then I get further states, an infinite tower of states with energies that are minus 1/2 1 over n squared. Okay? This is the well-known spectrum that Schrödinger calculated for the first time in 1925, I think. Okay? And it is precisely reproducing the old Bohr quantization rules, which were so successful in explaining the lines, okay, of observed from, I mean, the dark lines in the spectrum and so on and so forth, emission and absorption lines, okay? So in some sense, this was a remarkable achievement. By writing an appropriate differential equation, he was able to calculate that the eigenfunctions of this problem were having exactly the energy that Bohr was already, I mean, predicting, but with a theory that was kind of, I mean, not particularly fundamental, okay? So a very remarkable achievement. The only, we are kind of late. I just urge you to do the algebra, but I would like also to spend a couple of minutes more to understand the degeneracies. Because you see, if I have n equal 1, this is n equal 1, right? The ground.
Sorry, Professor. I think I'm sorry to say this, but the launch closes by 1, so and when Adrati goes through.
Then I think
it's fine. It's until 1:30, I think. It's
no, well, let's stop.
Okay.
Okay.
Do you have a couple of minutes, or we stop here? We can stop, huh?
I think we can continue since it's like 1:30.
Okay, just 2 minutes.
Yes. Yes.
So n equal 1. Remember, n was the sum of this strange integer k, okay, which was greater or equal to 1, plus the orbital angular momentum 0. Now, if n is equal to 1, since k has to be greater or equal to 1, you immediately deduce that L has to be equal to 0. So this state here has L equal to 0, is the S state that we were discussing in the guest state that I produced for you, okay? And it is only one state. It has a precise wave function you can write in the notes. It's given is the decaying exponential. We just looked at it in the initial exercise, the simple exercise. Okay, good. So this is simple, the famous R radial function proportional to e to the minus rho. Very good. Now we look at n equal to 2, which is this object here. N equal to 2. Now, if you want 2, you can have 2 in two possible ways. I can take k equal to 2 and L equal to 0, or I can take k equal to 1 and L equal to 1. For the energy, makes no difference, okay? Because what it counts is the sum. Remember that the energy depends on the sum, n squared. By the way, this k, n, and L have names. This is the orbital angular momentum, orbital quantum number. This is so-called a radial quantum number for a reason. It tells you how big is the polynomial. Remember that this is controls where the polynomial has, how many terms you have in the polynomial, in the radial polynomial. And so it's called the radial quantum number. And this is called the principal quantum number, because it's, after all, the sum of these two quantum numbers, but it's the one that enters into the energy, really. Okay? And this suggests that this state here, the n equal 2, if I look more closely, is actually two states. One is an S state, is the 2S states. And the other is the 2P states, because it has L equal 1. You see, this is the 2S state, and this is the 2P state. They are degenerate, okay? So I draw them at the same energy. In fact, the 2P, you know, it's not a single state, it's 3 of them, right? You remember? So the structure of the spectrum is in fact even slightly more complex. There are 4 states that are totally degenerate, because the L equal 1 comes with m equal to +1, 0, and -1, and they are totally degenerate. So the 3P states. Okay, is it clear? And so on. You can proceed with larger n, and you discover that for n equal 3, you have 3s, 3p, and 3d. Okay, so for n equal 3, 3s, 3p, and 3d states. Okay, so familiarize a little bit with this construction and names of the states, and the fact that there is in fact this interesting extra degeneracy associated to the very special nature of the hydrogen atom. Okay, I will stop here, okay, because we have gone a bit longer than expected. Okay.
Yeah. Excuse, Professor.
Yes.
Yeah. Apart from painfully doing all the algebras,
yeah,
I know particularly thinking from, because there are different algebras, from the one we encountered in angular quantum momentum, we're having these Legendre polynomials, and here we're having these Lsquare polynomials and all. Yeah, I understand that, okay, we can do this on our own, but also remembering them will be a little bit difficult to always know what
you
the
don't
polynomials
have to remember. There is Google remembers for you.
Okay.
Remember,
Yeah.
it's true. These polynomials that you find the radial function are called Lsquare polynomial. But who cares? Obviously, yes. They are some solutions of a particular differential equation, which is the differential equation we wrote, by the way. Okay, so
Yeah.
correct. They have the names, and you can obtain them by just looking into Google. I just wanted to give you a flavor of the fact that if you are alone on a desert island without Google, okay, you can read the algebra yourself and make sense of the spectrum of the hydrogen atom and of the form of the radial wave function that comes out. Okay, this is the only message that is coming from the algebra. Then the algebra is associated to names of these polynomials, which you can search with Google's, and everything would come out automatically. Okay, but you need to have a Wi-Fi connection for that. Okay.
Yes.
Good. That's it. Okay.
Yes, Professor. Thank you.
Sure. So I'll see you next
Week.
Next week. Yes. Okay. Bye-bye. Ciao.
Ciao.
Ciao, ciao.
Bye.
Bye.
Goodbye.
We can get the record in. I think you recorded, right, Professor?
No.
No, the system. I mean,
Okay. Okay.
In any case, I have the PDF of this that I wrote in the share screen, and I can send this PDF of the share screen to you. Okay?
Yes. Yeah. We appreciate it too.
Sure.
Yeah.
Okay.
Thank you. Bye.
Thank you. Bye bye. Ciao.
Ciao.